So in the last video we talked about ionic bonding, which happens when two very different electronegativity atoms get together. And so one ends up ripping an electron off the other, and electron transfers take place between a metal and a non-metal in order to satisfy both atoms. But what if you get two non-metals which are equally unwilling to give up electrons? You know, these are two people who are like, you know what? I got my electrons, I need more, I ain't gonna give it up. You know, this is what I got, and I actually need more. You're not taking it from me. You're not taking it from me. No way. So instead of arguing, they decide to share electrons. And so these are covalent bonds, and we're going to be formed between two atoms which are basically sharing a pair of electrons. Okay, so this is going to happen between nonmetals, and where there's going to be small differences in electronegativity, basically. Okay. Now, look at these two atoms up there, for example, okay? Each of them has 7 electrons in its last shell, okay? So we're talking about chlorine here again, the same guy from last time. So that means you got chlorine and another chlorine. Now, chlorine says, you know, I need one more. Or the other chlorine says, I need one more. But you see, they're both the same atom. They have the same electronegativity. There's no way one is going to rip an electron from the other, so they're going to be able to share this electron. So basically, you know this extra electron that each one of them has that's actually making them miss an electron here? They're missing one. So if one shares one with the other and the other one shares one with the other, this 2 electrons here will be shared equally between them, and they will count for both. And that will stabilize the electron clouds of the atom, and you're going to have the formation of a electron pair share, we call it talking about. Now, this will actually create the kinds of bonds which will stabilize the cloud. Now, notice, by the way, that one side will have more concentration of electrons than the other, okay? And you see that happening there, which will create kind of like dipoles. We'll talk about that, all right? But either way, still, this is going to be shared of electrons. And this is going to be important later, the dipole thing I talked about. But either way, look at the hydrogen atom. Same kind of thing. You have one hydrogen atom with only one electron. There's no way he's going to give this up if he meets another hydrogen atom. But if each hydrogen atom shares each of their electrons, they actually form an electron pair share, and that forms what we call a covalent bond. Now, one thing you need to know about when doing covalent bonds is that it's the Lewis model of the atom. Now, you know how the Bohr model, you put these electrons in these little layers like that? In the Lewis dot model, what you do, for example, with hydrogen, since it only has 1 electron, you put a dot like this. But if you did helium, which has 2 electrons, you're going to put 2 dots like that. Okay? Now, if you're doing lithium, which has 3 electrons, only 1 in its last shell, you're also going to put 1 dot. So what you're doing is you're putting a dot to represent the last shell. If you do oxygen, for example, which has 6 electrons in its last shell, you're going to have to put only the last shell. 1, 2, 3, 4. Notice that you put them in opposite ends to avoid each other. Then you start pairing them up once you get all the ends taken. So you're going to put 4, 5, 6. And that's going to be the electrons. Which means 2 of the electrons of oxygen are going to be unpaired and available to actually do bonds. What this actually means is that these electrons will be in orbitals by themselves, which means they can actually share this orbital with another atom, allowing themselves to be paired up. And that's actually what's happening to the hydrogen atom in this particular example here. It's got 1 electron on the s orbital, and another hydrogen atom also has an electron on the s orbital. And so what they're going to do is they're going to merge their s orbitals like this, and so that they're indistinguishable from each other. And then they form a covalent bond that can be represented in a Lewis dot like this, okay? Or with a covalent bond symbol bar, which is this. Now each dash represents a pair of shared electrons, so therefore it's going to be a single covalent bond since only 1 electron is shared. Same thing there with chlorine. They're merging one of their p orbitals, okay, in this case. But either way, because look, chlorine will have 1, 2, 3, 4, 5, 6, 7, 8. Pair up, fill up your s orbitals. Then they still have 2 more to be put in, so they fill up 2 of the p orbitals, and then you want to have the s orbital, another p orbital left. and they will merge those p orbitals together to create a covalent bond, which actually looks like this. So now they will each look completed on the Lewis dot model. Okay, and remember, those two electrons in the middle count for both, and that's why they're both happy. Or you can represent that as a single covalent bond between the chloramine atoms. Now, these are single covalent bonds because only one pair of electrons is shared. But some atoms actually share two pairs of electrons. Look, for example, when two oxygens meet. Okay, when two oxygen atoms meet, remember, oxygen have 6 electrons each. So 1, 2, 3, 4. Pair the s orbital and one of the p orbitals, which means 2 p orbitals available for bonding here. Okay, so they're 1, 2, 3, 4. All right, 5, 6. Now, what will happen then? If you're bonding 2 oxygens, these two will connect, and these two will connect. Okay? And that means you're going to end up with a double covalent bond, where 2 p orbitals are shared, and it will kind of look like this if you do the covalent method of formula. Two lines, each representing a pair of shared electrons. So they're sharing a total of 4 electrons between the two of them. And you see other variations of this. So you see that here, the difference between a single covalent bond and a double covalent bond. You see that? And here you see more examples of these double covalent bonds right there. On the carbon dioxide are bonded by a pair of covalent bonds between carbon atoms and oxygen atoms. The carbon has 4 on this last shell, and oxygen has 2 each. So you're going to be carbon with 1, 2, 3, 4. And then an oxygen, which has 6, right? So 1, 2, 3, 4, 5, 6. Same thing on the other oxygen. 1, 2, 3, 4, 5, 6. So that means the carbon can share one over here and share one over here. That oxygen has a total of 8 now because it counts for both. So he's happy. But that oxygen is not happy yet. But it's okay because this carbon is not happy yet either. So you can bond these two together and kind of connect them. And you've now made a covalent bond between them. And we represent them in this form here if you're doing covalent method. Now you see these are examples of double covalent bonds. And because they're double, they're going to be stronger than single covalent bonds. You also have triple covalent bonds, and I'm not going to draw this one, which is representing in a line formula, but I'm going to draw this one there. Look at the nitrogen atom, okay? Nitrogen atom, Lewis dot. It's got 5 on its last shell, so 1, 2, 3, 4. Pair up an s orbital, good. The other nitrogen atom, 1, 2, 3, 4. Always separate the atoms, and then I'm going to pair up one of the s ones. That means I have 3 available p orbitals to actually form covalent bonds. And so there you go. I'm going to put them together. So these two get shared. Now each atom has 6. These two have shared. Each atom has 7. These two have shared. Each has. So in order for nitrogens to make each other happy, they have to share 3 covalent bonds, which means a triple covalent bond between them. And it's the same kind of thing that's happening right there between these 2 carbon atoms. Notice that since carbon has 4 electrons on its last shell, it needs to bond 4 times to be happy. Look at here. It's bonding 1, 1, 2, 3, 4 times. This one also bonds 3 times here plus 1 time there. Look at this one. 1, 2, 3, 4 bonds. Carbon always bonds 4 times in order to be happy. Look at nitrogen. Since it's got 5 on its last shell, it needs to bond how many times? 3 times in order to be happy. Oxygen has 6 electrons in its last shell, so it needs to get to 8, so it needs to bond twice to be happy. So you see, the number of valence electrons will determine the kinds of covalent bonds you make. So again, the valence electrons are going to be important to determine this. Now remember, triple bonds are going to be even stronger than double bonds because they're actually sharing 3 electrons. Alright? So, alright. Then you also have all of them gathered up here. See? Single, double, triple. Remember, the strength is increasing as you go towards here. Hydrogen gas held together by single. Oxygen gas held together by double. And then nitrogen gas held together by triple covalent bonds. And you can actually see how to represent this with Lewis dot, with lines. Or, I'm going to write down the actual chemical formula. N2, O2, or H2. Now remember, because hydrogen has one electron in its last shell, it can only make one bond. Since oxygen has 6 electrons in the last shell, it needs 2 more to be happy, and it will make 2 bonds. And that's what you see up there. And nitrogen will make 3 bonds because it has 5 electrons in the last shell, and it needs 3 more to be happy. And so the number of valence helps determine what happens in a cloud.